Okay, well, thanks everybody for joining. Again, this is almost record number, aside from maybe the first one that we had. Then it was in the pandemic, so there was many more people online than what we even have in the room right now. But thanks for everybody for joining us today. We have certainly a special visitor here today, and we're going to talk about ionospheric plasmasphere modeling. Dr. Joe Huba, who as many as I sent out incorrectly that you were with NRL, but long time with NRL, but now with Syntek Technologies. I'll leave it to that. And without further ado, I'll let you get going. It's just a time.
Thank you. Okay. Thank you for having me. I heard there was drama yesterday that the faculty were trying to vote me and oust me from being speaker, but I prevailed, so I'm speaker today. Bad joke, sorry. All right. I've given some of this to a variety of people over the years. So modeling the plasma regularities in the ionosphere and plasmasphere. So it's like two talks in one. And I kind of always show this to highlight, what we're talking about in terms of these equatorial plasma bubbles and irregularities. And this is a animation from John Makela with an all-sky camera in Hawaii. And you're looking at emissions from a 557 line. And where it's bright, there are electrons, and where it's dark, there are no electrons. So when one plays this animation, you see these dark features come up. And these are these equatorial plasma bubbles, the regions of very low electron density. And you can also see that they're highly structured, or relatively speaking, with bifurcations and things coming out of the sides. So the other interesting thing that is here is overlaid are colored lines, which are orbits of the GPS satellites in the field of view. And if I stop around here, so here this blue satellite signified by the symbol, the GPS signal is passing through this disturbed region, this equatorial plasma bubble. And down below in the lower right, they're making relative measurements of TEC from the signal. And you can see that, there's a little dot here, then it goes blank, and then it recovers again. So this particular time, they've actually lost the signal from this GPS satellite. So this is sort of highlights what we're doing and what we're talking about in terms of space weather effect. And aside from possibly disrupting GPS signals, it also affects communication symbols. So these bubbles, they're large scale, tens of kilometers. So you have bite outs of 2 to 3 orders of magnitude of electron density. It's a major component of more generic term equatorial spread F. And for equatorial spread F, you actually can cascade turbulence down to 10 centimeters. So we're just focusing on large scale, but there's a whole plethora of instabilities that go on over this region. So the conventional wisdom was this is generated by so-called generalized Rayleigh-Taylor instability or interchange instability. And so this comes from Women in a Hose in 1976, which is a cartoon of what they imagined could happen. And this is the F region. This is the high density region. This is lower density. This is lower density. So the density gradients pointed up on the bottom, pointed down at the top, and gravity is pointing down everywhere. So where you have gravity and the density gradient in opposite directions, that gives rise to an interchange instability, or possibly an interchange instability. So this had been, promoted or suggested, but then it got poo-pooed because they said, well, we see turbulence on the top side and it's only unstable on the bottom side. And so what Woodman and Hose was proposing was actually you generate a large scale bubble, but this bubble can actually rise and penetrate to the top side, and that's how you get turbulence on the top side. So back in '76, he suggested this to Sydney Ossicow, and they have a research lab, and they ran a simulation, and for the first time ever, they showed that this could actually happen. You can generate a bubble below the F peak and were to rise above the F peak. This is data from the CNOS mission, Chaosung Wang. I'll just focus on the middle panel. This is 4 success passes. And the point is simply, in situ, they see these really large bite outs in the electron density. Again, 2 to 3 orders of magnitude in scope. And they're quite extensive, and they persist for quite a while. And it's these, features we're trying to model, as well as to hopefully someday forecast. Okay. All right, so most modeling today by myself and others, rather than try to model the entire globe and do itself consistently with everything, what was done is for computational regions, you just take a small section of the ionosphere, like this little like flux tube-like region here, maybe going from 90 kilometers to a couple of thousand, plus or minus maybe 30 degrees or so in latitude. And just measure or model the possibility of turbulence in this region. So this is work we've done years ago, and these are just contour planes and an isosurface. And then here you can see, like, it's hard to see, but this bubble rising up, and then this is an isosurface. So this is a very low density region that has risen above the F peak. So this is, kind of pretty good in everything. You can get these features, and some other simulations are much more dramatic in terms of structuring, but it doesn't capture the global ionospheric state, the global density, E plus B drifts, and all the other ingredients that either contribute to this instability or not. So, so recently, in the last few years, we've joined forces with some thermospheric modelers. We're using the SAMI-3 model developed at NRL by myself and Glenn Joyce. And then also WACM-X, this is the MCOR whole atmosphere model that extends up to about 500 or 600 kilometers. Boom. And it calculates neutral composition, temperature, and winds, and parameterizes gravity waves. And also working with Erich Becker and Sharon Vadas. Erich has a code called HIA MCM, which is a sort of a German whole atmosphere model that he's extended up to 450 kilometers, and actually simulates gravity waves from first principles rather than just parameterizing it. So what we've done is we one-way coupled the codes. We take the thermospheric variables from WACM-X as well as HIA MCM, and then we feed them in the SAMI-3. But there's no backtalk. SAMI-3 does not provide information to these thermospheric models yet. So in terms of spatial resolution, the WACM-X results I'll show today, the longitude resolution is 0.625 degrees and latitude is less than a half. So we have a grid scale of on the order of 70 kilometers or smaller globally. I'll show a little bit from high MCM, but they're a little bit finer scale at a half a degree. So we have 50 kilometer grid resolution. For SAMI-3, we use the same longitude gridding as WACM-X and high MCM. But for our latitude grid, it's non-uniform. It's relatively fine near the equator, and then coarsens out as you go to high latitudes. And the reason for this is to capture the dynamics in the equatorial region to generate the E cross B fields from neutral wind dynamo. I believe these are the highest resolution simulations done to date with a global ionosphere and thermosphere model. And just as an aside, we also have a flux corrected transport scheme to reduce numerical diffusion. So in terms of how does the thermosphere affect the ionosphere, the primary drivers would be the fluctuations in the neutral wind associated with gravity waves. And so this tries to highlight how actually you're affecting the ionosphere. So on the bottom, we have the velocity equation. And there are two places the neutral wind comes in. The first is direct ion neutral coupling between the ions and neutrals. And the second way is through the electric field, where when you calculate the field from electrostatic potential, one of the drivers is the neutral wind at low latitude. So if you modify the neutral wind, you modify the potential, you modify the electric field. And so then the impact is shown in these contour plots above. So this is a simulation that was done years ago. What we're modeling was the impact of the Tohoku tsunami that generated atmospheric waves on the ionosphere. So we used an analytical model to generate the perturbations associated with the tsunami in the ionosphere. And in the upper left here, the color is the neutral wind that's been modified by the blast wave, so to speak, where red and blue is up and down the field line. And then on the bottom left is the ion velocity, and they pretty much match 1-to-1. So it just shows this term down here, this ion neutral coupling term is so strong that when the ions move, it just takes the ions with them. Then the other interesting feature is in the upper right, the perpendicular variations in the neutral wind can also generate this electric field. And this electric field can actually map all along the field lines to the conjugate region, because the field lines are essentially equipotentials. And so this is the plasma velocity that's been generated associated with this wind field. And even though it's an order of magnitude smaller than the parallel motion, it still has far-reaching effects. And then the bottom right is the impact on the density. It's oversaturated, so major perturbations are locally where you have the localized nature of this disturbance, but also in the conjugate region, tens of thousands of kilometers away, you can also perturb the density. So even though you might be perturbing the system in one place, it can have far-reaching effects. In fact, going to high altitude and to the conjugate region. So this is from high MCM, and this is the vertical neutral wind. It's plus or minus 5 meters per second. And the purpose of this is just simply to show the spatial temporal variations associated with gravity waves in the neutral atmosphere. So there's also fluctuations like this on the neutral zonal wind and Morale wind, but they're much stronger. And they would have to be filtered out to see this. But the point is, it's relatively small scale, 100 kilometers, and it varies. This is on every 15 minutes, so it's pretty dynamic. So it's these variations in the winds that can affect the ionosphere. Stop. Okay. So this was the first simulation we had done with Wacom X, and this is a equinox case in March at low F10.7. Top panel is SAMI3, but it's driven by empirical models. IMSIS is an empirical model of the neutral composition and temperature, and HWM14 is an empirical model of the neutral winds. And they don't have any atmospheric waves or anything. They're relatively smooth. So in this top left panel is the total electron content. And it's just relatively smooth and what one would expect. But in the bottom panel, we're driving it with Wacom X. And although overall it looks like the top panel, what stands out are these striations in the Atlantic sector, which are these equatorial plasma bubbles that developed. Okay, so the point here was simply that these are developing where we have seeds generating, or wave seeds generating that the instability can build off of. Another feature, these bright spots at mid-latitude And we haven't looked in them in great detail yet. They don't show up for the standard case, but these appear to be related to sort of plasmasphere drainage during the daytime.
Everybody turned their phones off. Surprised they didn't get all going at the same
Wow.
time.
Let's just pause.
Yeah.
Take a pause for a minute. Do you have, I should have mentioned there's cookies available.
Anyway. So anyway, during the daytime, you can build up plasma at higher altitude, and at night, these regions become low pressure and plasma drop down along the field line and create these enhancements. And there have been some observations of these nighttime mid-latitude enhancements, but this is something requires some further, looking into. So then it just turns out, or necessarily coincidentally, but fortuitously, the gold satellite was up and making measurements at this, well, not the same time as our simulation. This is in October, and they noticed these striations again occurring in the Atlantic sector associated with these bubbles. And then in our middle panel, we generated the emissions to correspond or compare to what was observed by gold. And again, we see the striations in roughly the same place, but the intensity of the emissions are weaker by a factor of 4 or so than what was observed. And then the far left panel, I just changed the color scale to highlight the equatorial anomaly and then the striations here that are seen here. So this was, again, we weren't trying to model this particular day or anything, because we didn't know about it when I ran it. But it is both in equinox conditions and it's both for low F10.7. So the generic conditions are roughly the same. So this was more than a pleasant surprise. So this is a different case. This is December solar max. And the top panel is the electron density as a function of longitude and altitude. And the bottom panel is the E cross B drift at about 350 kilometers at the magnetic apex. So during the daytime, where we have all the electrons, the E cross B drift is nominally upwards. And then at nighttime after sunset, it's nominally downward. So the ionosphere kind of breathes up during the day, down at night. But at sunset, you sometimes have the so-called pre-reversal enhancement, this larger drift than during the daytime. And so this is one of the key features of the so-called equatorial spread F, or generation of equatorial plasma bubbles, is that this pre-reversal or post-sunset enhancement gets really large, you trigger bubbles. So in this animation, as we go along here, the drift is about 20-25 meters a second. But then here at the end, in this region here, it gets large. Here it's about 40, it goes up to 50. And as this drift is going upwards, it's lifting the ionosphere up, and lo and behold, bubbles form. So this is sort of the standard picture people have talked about for years. And this post-sunset region, you can generate these bubbles, and it's associated with this upward drift. So that's good, right? So this is June solar max. So if I play this, if I stop here, again, what we see is this drift. It's approaching 50 meters a second, and we're getting some upward things, but no bubbles ever form. You get some fluctuations, but no bubbles. So the idea that you would say always need a large upward drift to get a bubble, or if you do have an upward drift to get bubbles after sunset, isn't always the case, which is well, interesting. But I want you to all the different results we've done for these systems. And I just highlighted, you know, 2 or 3 here. This is a contour plot from Burke et al. The early 2000s, and it's longitude versus day of year. And their contour plot of the likelihood of seeing equatorial spread F with these bubbles. And so in the Atlantic sector, in the December timeframe is when you're most likely to see it. Then when you go into the summertime here, that's when it's least likely to be seen. And if you do see it, it might be over, say, Africa and in the Pacific sector. And so these labels are from our simulations, and the label indicates where we saw bubbles. So I showed the animation of the December solar max case, and we saw bubbles forming in the Atlantic sector. I didn't show December solar min, but we saw bubbles here. For June solar max, we didn't see any bubbles. So that kind of fits with this idea. This is the least likely time to see bubbles. For the equinox cases, September and March. For September, we saw them here and here, and for March, these in the locations here. So again, that's overall consistent with this climatological picture put together by Burke et al. And then lastly, we also did see some bubbles form in the summertime in August here and here. So generically, the Whack-a-Mech SAMI3 model seems to be capturing, in the limited number of runs we've done, pretty well with climatology. It's kind of, but it's relatively easy, I think, maybe to explain this December solar max, as I said, associated with the C plus B drift. Why you don't get the bubbles in the June solar max case, even though you had a big E plus B drift, still needs to be looked into. I don't have an answer for that. So just to summarize this section, we've done a lot of work recently, the last few years, of SAMI3, Whack-a-Mech, and high MCM. We're able to capture the onset and evolution of these bubbles. Atmospheric waves naturally provide seeds for the instability, and we're seeing day-to-day variability and longitudinal variability in these simulations, associated with the fact that the atmospheric waves can change on a day-to-day basis. I haven't shown it, but some of these bubbles at times rise to quite high altitudes, over 1,600 kilometers. And I didn't discuss this either, but you do get bubbles forming after midnight, and these can convect into the day side, and you can have daytime irregularities in the top side in the morning. So, you know, we have an ongoing program to do this and to do more simulations and more event comparisons and comparing to gold and icon data and things like that. So far, this has proved, I didn't predict this was going to happen. A lot of these results were just complete surprises, pleasant surprises, I'd say. Okay, so that's what I wanted to say about the ionospheric irregularities. So now we'll move on to the plasmasphere. So essentially, the plasmasphere is the extension of the ionosphere unclothed field lines to high altitudes. This is from the image satellite helium plus. So this bright green region is the plasmasphere. The boundary between the inner magnetosphere and the plasmasphere is called the plasmapause. It's high density. By high density, it's more than 100 per cc, and it's relatively cold, maybe up to 30,000 K. Predominantly hydrogen with 10% helium, which is why we have this picture. And during storm times, O plus can manage to get into the plasmasphere. And then this plasma pause can range between 2 and 7, L equal 2 and 7, but nominally it's further out 5, 6, 7. During storm times, it erodes and you come closer to the Earth. And it's a collisionless plasma. The lower right is just a schematic or that I found online, and it's sort of like I would say a canonical type picture one would see as a plasmasphere. That's a big donut. It's nice and smooth and just enveloped the Earth relatively uniformly. So then this is now 8 years ago, in 2015, my brother sent me an email with the question, real or crap? And then there was a link to go to it to see what my opinion would be. And this was the link. Giant plasma tubes floating above the Earth. I did a really spectacular graphic on, but even a cool title. But so this was put out remember by a student out of Australia using their radio astronomy array. Using interferometry, they made a lot of measurements of plasma motions in the ionosphere and piecing together this data, then they presume that this is what the density looked like in the ionosphere. That you had these enhancements of tubes or whatever, ducts of plasma. So one reason that people would actually think this is actually really real is, I won't talk about it in much detail, but there's been a lot of work with VLF and Worcester wave propagation in the ionosphere and plasmasphere, and there's ducted versus non-ducted propagation. And so if you do have like this duct-like feature here, it allows waves to propagate freely along here. Although they can diffuse out, but they're used to guide the waves. So I'll skip this picture. All right. So I showed the first simulation where we had the ionosphere bubbles look like, say, the gold images. So this is the same set of simulations, except now we're looking at isosurfaces of the electron density at 5 times 10 to the 3 and at 1 times 10 to the 3. On the left panels is SAMI3 WACM-X, and the right panels is SAMI3 not high MCM, but IMSIS and HWM. So when you're relatively enclosed, about L equal 2, again, you can see that the ionosphere with the atmospheric waves presents these corrugations and some duct-like structure. On the right, it's a relatively smooth feature. You do these diurnal effects from the plasmasphere, sort of filling in and refilling from day to night. The bottom panel on the right, is, I would say, what normally people would think about, that the ionosphere was a big donut. And then people pointed out to me when I've shown that not a donut, but more of a pumpkin. So, so that was pretty interesting. So again, all of this behavior structure is associated with actually atmospheric waves. Okay, it penetrates all the way up into space. So these are just line plots of the electron density as a function of longitude. The red curve that's relatively smooth is the empirical models, IMSIS and HWM. And the black curve is with WACM-X and SAMI3. So the point is, you can see relatively strong variations, but almost a factor of 2 or so in longitude as you go around the Earth. Then higher altitudes, and there's a lot of structure associated with the WACM-X, and maybe a little tiny bit with the higher MC or with IMSIS HWM, but part of the structuring at this higher L show is associated with high latitude dynamics of the potential there. Okay, so here the top panels are from press. So here's L equal 4. These are press measurements of the electron density, again, as a function of longitude. And then the bottom is from our simulation. And it really shouldn't be compared 1-to-1. I don't know if this press measurement was made all at once or was put together piecemeal as it passed through the appropriate region. But nonetheless, you have densities on the order of about 500 here, and here we have maybe 800. And you do see these fluctuations that are quite similar to what we see in the simulation. So, on the other hand, if you go closer to the Earth, at this particular time, the crest measurements, maybe around 1,000, relatively smooth, or models showing maybe twice as big in terms of the density, and there's actually structure associated with it that isn't seen here. Again, this is only one simulation, etc. But nonetheless, at least at the L equal 4, it looks really good. Here, not so good. So the other thing I had talked about were these ducts, plasma tubes that they talk about. So one way to diagnose them occurring is to integrate the electron density along a flux tube here. And we're going from 1,000 kilometers in altitude in the south to 1,000 kilometers in altitude at the north. We have the electron density, and then this magnetic term here to indicate how the flux tube changes inside as a function of the magnetic field. And then the second thing is to calculate, we'll say, fluctuations. You can calculate this dNt here, where we take the measurement, this calculated integrated flux, or integrated density, and then subtract off an average density where the NT is averaged over a 30-minute window. So you have these fluctuations, then you average, and then you can subtract to highlight the fluctuations. This is for the empirical models. We see these ducts, we'll say at high latitude. Again, this is associated with a high latitude convection pattern. And then there's something down here, which is associated with equatorial ionization press. But at mid latitude, there's really nothing here. And then below it is now the same calculation, but as a function of longitude and latitude. So this, you can imagine, is this slice here along the dotted line. So if you could take this plane and turn it, put it here, that's the idea of what it's looking like. So again, it's relatively bland. So this is the case with Wacom X. And now we see we have in the top panel a number of ducts. So I've labeled them 1, 2, and 3 here. Then in the lower panel, again, along this line here is again this plane just turned at right angles to go along here. And I've also labeled the 1, 2, 3 where these ducts line up down here, which is very hard to see, but this is 1, this is 2, and this is 3. The point here is if you say look at 2, you can see 2 is limited in L shell or altitude or latitude, but here 2 is also limited in longitude. So we have these closed contours, so there really are duct-like features. It's not like it's really spread out one way or the other. That these are, again, I'm repeating myself, could be considered a giant tube in space. So I've just, again, looked at this one longitude in the American sector. But you can see here that, these little ducts or whatever, occur, over quite a range and are quite extensive. So then this is some measurements reported by Claverd a number of years ago. And what they were showing here is, in this region here, there's a VLF transmitter. And then on Crescent satellite, Denver satellite, they had a receiver to receive the signal that was being generated by the transmitter. And here, they color code the most intense waves that they saw that were transmitted. And down here, they show where Cress and Demeter were, relatively speaking, and then here's where Demeter was. Okay, and so the point is, what they're arguing here is then that these waves in the L shell range 1.5 to 2.5 were ducted. This is where the ducts are. You certainly see waves elsewhere, but they are unducted. They can just cross the magnetic field line. So if you go back up to the previous view graph, these ducts, at least here, are occurring between, say, 10 and 40 degrees, minus 70, minus 50. And so here we have about 10 degrees to 40 and minus 70 to 50. So this is mid-latitude region where we're seeing these ducts generated by the waves. And then from these VLF observations, they also see ducts in this range. So, you know, things are, quote, consistent right now. Then the other question we looked at was, how long do these ducts live? So this middle panel is what I showed previously. The top panel is 15 minutes earlier. The bottom panel is 15 minutes later. And so this top panel I labeled 1, 2, and 3. So 1, there's actually no duct really. 2, you can see a duct, and 3. So they live on for 15 minutes. And then down here, we again have 1, 2, and 3. So there are still some ducting features, 15 minutes later. So for 2 of the ducts, they seem to live about 30 minutes and 1 maybe 15. So 30 minutes is pretty much the most we've seen. Haven't done an exhaustive study yet, maybe 45, but they have been reports that these ducts can last a half hour to 2 hours. So we certainly capture the half hour in some locations. I don't think I've seen this particular one simulation have them lasting 2 hours. But again, this is reasonably, quote, consistent with the observations. So, I think, yeah. So, we shown that these atmospheric gravity waves propagate to the thermosphere, disturb the ionosphere, and they can generate not only these equatorial plasma bubbles, but they can also generate these plasmasphere ducts at mid-latitude. It has been suggested also that E region plasma instabilities can also produce plasma ducts by generating turbulence or structures in the E region that map into the F region. And there's been some reports showing comparing data with observations that this is, certainly a plausible mechanism. The downside of this is this mechanism is only restricted to night times when you can have instabilities in the ionosphere, whereas with these atmospheric waves, they can occur nighttime and daytime. So we've seen some relatively modest agreement with limited data observations, and could be the cause for the ducting. And again, this is an ongoing investigation to look at seasonal longitudinal dependencies, and there's also been indications of perhaps electron temperature irregularities. I know this is a big downside, but be that as it may, even though we're doing global simulations at high resolution, or high resolution is still 100 kilometers or more in terms of scales we can resolve. And a lot of these irregularities, when they talk about ducts, they also have seen them at much smaller scales, tens of kilometers. So we're off by an order of magnitude in spatial scale with our ability to capture this in terms of such small scale stuff, but we're at least moving in the right direction. And then last, I've said this earlier, I'll just repeat it. the first simulation, I was just anticipating traveling on disturbances. Was not expecting bubbles, much less that they agree with gold or look like gold, and this plasma structure and ducts were surprised, and so if there's a quote on scientific surprises, I hope I haven't met it yet, but to date, I'm pretty lucky. So luck is good. So if there are any questions or comments.
Any questions, comments? Online as well, I'll try to monitor the chat.
So in what sense is the Rayleigh-Taylor instability generalized? How do you generalize it?
Yeah, I didn't show any equations. You look at the full growth rate equation, there's a term that G over L nu IN. So when you think of Rayleigh-Taylor, you think about G, gravity being the driver. Also in the equation, there's the neutral wind and electric field. So neutral winds and electric fields can also generate instability. So when the neutral wind generates an instability like this, it's called the gradient drift instability oftentimes. Also like so they have different terminologies. So by generalized, it just means it's general more than just gravity.
Okay.
It's other factors or drivers can come in. That's what it means. Yeah, I think.
So I guess the classic Rayleigh-Taylor is like oil and water, right?
Yes.
Yeah.
Yeah, I didn't quite show it here, and some of the studies, where we've actually made these calculations of the growth rate, and try to figure out which term is the most important.
Right.
For the limited stuff I've done, the gravity term is the most important to date, although the other factors can contribute.
But then back to not being able to explain why you don't see it in the summertime, maybe it's those other terms that are becoming more important or less important. Maybe. There must be some sort of feedback.
I have to do a little bit more work. There's I didn't emphasize or even mention it, but the meridional wind can play a significant role in this, and primarily by redistributing plasma conductivity.
Yeah.
And there are some cases we've seen where the meridional wind, say is equatorward, it reduces the conductance and bubbles can form. The growth rate goes like 1 over the, we'll say conductance. Conductance gets small, growth rate can go up. Conductance gets high, growth rate goes down.
Okay.
So it's conceivable then that, maybe in this June case, the conductance were such to be put high because of the winds. Again, I don't have a firm answer, but
Was that comparison with the gold data? Was that a special day in any sense? That was remarkable.
Well, it was the first gold picture I saw. It was the first simulation we had done. I said, wow. Yeah.
In the dry season.
Yeah, it's so, we see them. Well, I've seen quite a bit actually in the Pacific sector, but it's over the ocean, so it's difficult to certainly see them visually. Can't see them with gold, but with the icon or some other satellites, it's possible to make measurements there. We can pursue that.
I know the focus here is on the bubbles, and that day showed all sorts of bubbles, but a quiet day, does it have nothing going on? What's the range of bubble activity?
In summertime, you see no bubbles.
No bubbles, just one featureless.
Well, we've done limited studies, but the June case I showed, there were no bubbles. I did an August case, and I saw 1 bubble in the Pacific and a handful over Africa. And they weren't even terribly strong bubbles. Like the first one I showed for December solar max, the bubbles went above my upper scale of 800 kilometers. The summertime runs, maybe they got to 600. So yeah, there's a strong climatology that was
So if you're saying that in the model, can't you turn things on and off and try and isolate what it is that's producing them?
It's kind of easier said than done.
Yeah, okay.
You know, so, yeah, it'd be relatively easy. I haven't done it. I could turn off the meridianal winds.
Right.
They can be turned off. And then we can do a run. And see what happens. So that's a good point. Turning off the zonal winds, then you lose the electric field. You lose a lot of the macroscopic features that you need for the instability to go, you know, it's for the ionosphere to behave like the ionosphere. The other thing I haven't done, I started working on it is, you know, I showed the IMSIS and HWM, they empirical models. WACM-X, high MCM have the atmospheric waves. So I could go in, I started working on where you can run in and go and filter out all the waves. And say WACM-X, then run the model.
Right.
Then there'd be a one-to-one comparison, waves, no waves.
Right.
With basically the same drivers.
Yeah.
So that's, to your point.
Yeah.
Another thing can be done.
Do you get a donut or a pumpkin?
What?
Do you get a donut or a pumpkin, right?
Definitely, yeah. Well, it's come out to be Halloween. So
Yeah.
pumpkin pie.
Yeah, in your movies, you showed a movie, I think, with December, Solomon, Medium Solomon, right? You were showing vertical drift, if you didn't quite say where. And then on the top was, you know, your density versus longitude. And the thing that struck me is that you were running Solomon, so you get a nice big proverse. But sometimes you get this fluttering thing after the proverse has gone to multiple drifts. Is that a bubble that's starting?
That's the bubbles.
Yeah.
Yeah, it depends where I put the cut. I think the velocity was 390 kilometers.
Okay.
But yeah, when you go through a bubble, you get a big, and the bubble velocities can be a couple hundred meters a second. Actually, they can go to 1,000 meters a second on rare occasions.
In the model or just in observation?
Both. I'm not. Generally, on these global models, this type of stuff, we get 200 meters or 300 meters. When we did the limited longitude range bubbles, you know, what we did for a long time, there you could get maybe a kilometer a second occasionally. Yeah. Yeah, but the irony is you're inside a bubble and you get this giant velocity, but there's no plasma really there. It's very low density, so it's. It's not like the whole ionosphere is being disturbed at hundreds of meters a second. The top of the bubble rises, again, 40, 50, 60 meters a second.
These bubbles, that they're always conjugate between the hemispheres. If you have bubbles formation going on, it's going to be mirrored from one side of the equator to the other.
Pretty much, yeah. I mean, you know, they form at the magnetic equator. Yeah, that's where they form. And you just have, you know, field lines going down, and you have the electric field can map down. So you know, it's a conjugate effect. Yeah.
Did the details map so precisely? I didn't examine your plots
Well,
that closely, but is it like a mirror image in some sense? Or pretty much the reproducing
It
structure
doesn't.
down to a certain scale, and then something else takes over.
I'm not sure I'd say they're quote mirror images per se. You can have meridianal winds that are different on either side of the equator, which can move stuff up and down. So that would generate an asymmetry. Just recently, I haven't looked too much into symmetry versus asymmetry. So, yeah, it certainly doesn't have to be a mirror image. Yeah, so.
Can you go back a slide? There was one of your bullet points that caught my interest. It seemed to be an overlap with what we see with the radars. Plasmasphere ducts at mid-latitude, irradiant plasma instabilities, but restricted to nighttime. Why the nighttime restriction? I mean, is that
High conductivity
Observ-
kills all the instabilities.
Well, that's what we see with the radars as well. There's a category of backscatter associated with irregularities that are mid-latitude. You know, the subarrow very clearly. And they're a persistent feature of the observations, but only from sunset to sunrise, not on the day side.
Yeah.
And we attribute that to the conducting layer shorting things out.
Yeah, right. Yeah.
Can you say a little bit more about the role of the gravity waves? And you said that one of the models actually models gravity waves and the other one parameterizes.
Yeah.
So what's the distinction there? How do you model gravity waves versus parameterize?
Well,
Or is that a question for a different person?
right. That's not me, but be that as it may, the one difference between these two models, the WACM-X and the high MCM is in these gravity waves I showed, the high MCM, they have vertical winds. Stuff's moving up and down vertically. And it can do that because it makes a non-hydrostatic approximation. The WACM-X is hydrostatic, things are at pressure levels. So in order to get a vertical perturbation, there must be some parameterization or forcing to generate that. In the high MCM, because there is no restriction on whether or not this stuff can go up and down, it can go up and down if it wants to. So that's one distinction between the two models.
Okay.
Mention something about the lifetime of the ducts.
Yeah.
What is it determines that? What causes it to fade away? I presume it just sort of diffuses away.
Well, they show a movie. There's, yes, if you. If I made a movie of this bottom panel, it's very dynamic. So there's a lot of motion. So it's not that particular duct in this location. It may not die, but it may move somewhere else. But these observations, they up to 2 hours, it's kind of remarkable that they're playing that. But be that as it may, I'm just saying these ducts can stick around, but they can move somewhere else. And that's what when I talked about a duct lasting 2 hours, I meant for a half hour in the exact same location.
Yeah. Based on the observations.
Yeah. So. Yeah, I should have. This is rather dynamic. Again, it goes to that animation I showed with the IMCM gravity waves and the fluctuation of the vertical winds. It's very dynamic. Things are moving vertically, not vertically, but horizontally. So you see the same type of feature here.
Certainly shattering the notion of a smooth, unfeatured plasmasphere.
Yeah.
Which is kind of the textbook version.
Right, yeah. And then as exhaustive a search as I would like, but there certainly is a lot of observations that, it is not all that smooth. Yeah. Yeah, so this is an aside.
Wonder, did you validate that, what was the space tubes figure?
Not really.
How did you respond to your brother?
How did I respond to him?
Yeah.
Oh, I looked it up and I read the paper and everything, and I told him it was real, not crap. So, and there's also been work in New Mexico at the VLA facility down there by Joe Helmut. They've also reported a lot of these types of structures overhead, show them graphically like the picture I showed. But yeah, they've used interferometric techniques to track these structures and ducts. Yeah, so my side, I mentioned the plasmasphere is collisionless. Actually, I think I'm not positive, I'm 99% sure in all ionosphere models, this left-hand term is neglected. And because you want to do the ionosphere's collisional, you don't need ion inertia. And so then if you were to go into the plasmasphere and try to measure velocity, if you solve this equation for velocity, it goes like 1 over the collision frequency, and collision frequency goes to 0, velocity goes through the roof, so it's unphysical. So early, when Glenn Joyce and I at NRL were developing SAMI2, we threw this term away, as everyone else did. And then we built a model using techniques everyone else used, and it kind of worked, but not as well as we liked. So one day Glenn came in and said, hey, let's just add this term. And we'll just solve the damn equation, to hell with it, let the computer do the work. The payment is a small time step. So if you throw away the term, you can take a time step of minutes. You keep the term, you get time step of seconds. So computationally, from an efficiency point of view, the code ran a lot longer than most other codes, but we didn't, quote, care so much, it ran fast enough. So it was added for, quote, numerical reasons. That was the sole purpose. We didn't think, oh, we're going to add the term because we're going to model the plasmasphere, which is collisionless. So this was sort of a byproduct of this decision was made over 20 years ago, that we're able to actually do the plasmasphere and capture, storm time refilling and other things physically, because we had this term in our model along the magnetic field.
Does this relate to the numerical diffusion discussion point that you made earlier on?
Actually, no. Now that comes from perpendicular motions associated with E plus B drift, this picture up here. The idea is you have a low density, high density region of an interface, and you're moving or transporting it from the E plus B drift, and if you're transporting it, you can diffuse it. And these flux corrected transport things allows you to transport it and not diffuse it so much. So it's not the parallel motion we've keyed on here, it's the perpendicular motion.
Okay, maybe one more time for one more question. We are coming up at the top of the hour. But certainly with discussions around here, just to wrap the seminar, at least portion up. Any other questions?
The old guys have kind of done.
Yeah, sorry.
Students want to say something?
Yes.
No pressure to not be graded. Well, thanks everybody for joining online and here. You help yourself to a cookie or doing it on the way out.
Did you get any questions online?
I didn't see any on the chat. Hopefully they're hearing us, so hopefully we're hearing them. And I didn't see anything, so but a couple people have joined, they're dropped off already from online.
Yeah.
But this is the announcement for the seminar part of it. We won't have one now for another 3 weeks. Sort of selfishly, because I will be the next 2 weeks, I'll be involved with travel going out to the annular solar eclipse in the Southwest. And so I will be back here in 3 weeks. Thanks everybody for joining. Yeah, you're welcome to stick around for other discussion.
And thank our speaker.
Yeah, thank you.